opportunity to give a talk. I will be speaking about orbital physics, but in connection with magnetism, and I'm sure I can profit a lot from the pedagogical lectures which were already given to you, but I will still try to go slowly and try to explain all of this. If you don't understand or you have a question, please stop me at any moment. Okay, so after pedagogical introduction, I will present some recent results, and these results are done mostly in collaboration with these people, with Jeremy Chen, with Hao, and with two Georgian physicists, George Baeza and Alex Magnetis. I think you know these names. And I will show you where these people appear. Okay, so this is the outline of my talk. It's a little bit extended comparing with what I put in the announcement. So I will also talk a little bit about manganese vanadium 204, which was not announced. So I will do introduction, and then I will speak about 3 different vanadium oxides. 2 of them are spinel, and another one is distorted lattice, this one. And I will show you that if any of them, each of them, the interplay between orbital and spin degrees of freedom is important, and without this you cannot understand neither the phase transition nor the ground state phase diagram. And at the end, I will show you that usually, probably most of you knows that spin orbital systems are very complicated, and at the end you want to simplify it as much as you can to get some analytical results and probably to understand physics better, even if some simplified model as ours are not directly applicable to some compounds. But still we can learn quite a lot by studying. Okay, as I said, this talk is about spin orbital system, and all these systems are on frustrated lattices, and the frustration of the lattices, geometrical frustration in the spin sector, is usually leading to the fact that the system cannot find a unique state, and there is some residual degeneracy, and different systems fight with this degeneracy in different ways. And today I will talk only how orbital help system to remove this degeneracy. Okay, so as I said, I will be talking about vanadium system, and in this talk only about this system where vanadium is in the 3+ state, and that means that we have 2 electrons in the d level, and because of strong Hooke coupling, they are coupled to spin 1. So it will be the orbital physics coupled to spin 1 physics. And this probably you saw already. So we have 2 electrons, and if you take a single ion, then these 5 d levels are degenerate. Whenever you put it to the lattice, there is some crystal field splitting, and already the cubic crystal field splits these 5-fold degenerate levels into low line T2G manifold and upper line EG manifold, all together. It actually depends on the ligand surroundings. So if the field is octahedral, then it's like this. And Jeroen in his talk was talking a lot about the EG orbitals. And in my case, I have 2 electrons. This crystal field splitting is very large, so I completely neglect EG physics, and I will be talking only about physics which happens in the T2G manifold. And there are some similarities, but basically many things are quite different. So we have these T2G states, and it was pointed a long time ago already by Abraham that in principle spin-orbit coupling do not need to be quenched in such a compound. And in fact, because this crystal field is very large, and you can really forget about these EG states, then you can project spin-orbit coupling to the T2G manifold, and it will behave such as the orbital angular momentum is not 2, as we would suppose for d electrons, but actually 1. And here is how the real orbital angular momentum is related to this effective orbital angular momentum, where alpha is just a constant, and for vanadium compounds, it's nothing else as 1. Basically, if you want to obtain this constant, you have to project spin-orbit coupling in the T2G manifold and do this projection carefully, and then you can actually get this. Okay, so in some compounds, for example in zinc vanadates, then the ground state, I want to say that if this spin-orbit coupling is very strong, then the ground state will be entangled state of spin and orbital degrees of freedom, and it can be, for example, effective J equal to 2. And in that case, if we study the ground state and the excitation, they will be quite different from both the magnons, which would be excitations of only spin degrees of freedom, and orbitons, about which you heard from Jeroen, which would be excitation of orbital degrees of freedom or orbital angular momentum. It will be some complex excitations about which I'm not going to talk today much, or maybe only at the end. Okay, in any case, we want to include orbital degrees of freedom into the description, and if we are talking about the more insulating states, then the orbital degrees of freedom in T2G manifold can be described by pseudospin, and this is pseudospin 1. So while 1, because if these 3 levels are completely degenerate, then there are 3 levels, and that would correspond to 3 projections of this pseudospin 1, plus, minus 1, and 0. Okay, orbital degrees of freedoms know about light. And how do you know about this? Whenever some distortion takes place, then the orbital level splits. And at that moment, we don't have any more free-fall degeneracy in the T2G manifold, but probably there is some splitting. What kind of splitting are usually taking place? So, if we have tetragonal distortion, you can think about this like take this and elongate it, for example, along Z axis. So, certainly all the orbital states which has Z component will be high in energy, while the orbitals, in this case XY orbital, which doesn't have any Z component, will be the lowest energy state. Of course, the EG orbitals, which Jeroen was talking about, also splits according to this kind of distortion, but as I said, today we will be talking only about T2G manifold. So this is tetragonal distortion, and that corresponds to the flattening along Z-axis. And if you want, you can further distort your lattice, and then it will be orthorhombic 1, and in that case, all these 3 levels will be non-degenerate. Right? So if you have 2 electrons, then in that case, you will occupy the lowest energy level first, so you put necessarily 1 electron here in XY, and you can put 1 electron in this doubly degenerate manifold, XZ and YZ. So if you would like to describe this degeneracy, then instead of using the pseudospin 1, you will need to use pseudospin 1/2, because the degeneracy will be only in this level, and I will talk about this. So what other type of distortion can be? So we can have still tetragonal distortion, but different. We can elongate along Z-axis, and the picture just flips. Once again, it can be some further orthorhombic distortion. But especially when we are talking about the spinel structure. In spinel structure, not only tetragonal distortion took place. Actually, intrinsic to the spinel structure is trigonal distortion. And trigonal distortion occurs, so this is the parahole lattice. If you take one tetrahedra and you start distorting the system along local 1-1-1 axis. So you can take any 1-1-1 axis, distort the system, and basically you can have the same kind of splitting, but now you have to rotate your orbitals, they are cubic orbitals in the space, in order to obtain the proper representation for the trigonal distortion. And you can do it like this. So you can use the chiral basis. It's nothing else that each of these orbitals are linear combination of cubic orbitals xy, yz, and zx. And this mu x, mu y, and mu z is nothing else as the coordinate of the local trigonal axis. In the parahole lattice, it will be interesting because you can distort the direction of the trigonal axis at each side is different. So you can see that at this side it's pointing in this direction, in sides 2 it's pointing in this direction, here and there. So at each side, trigonal axis, local trigonal axis point differently, and that's very different from the usual tetragonal distortion, where the tetragonal axis is homogeneous and is exactly the same at all the sides. And that actually brings some new physics in this compound. Okay, so here you can write the basis like this doublet, e.g. doublet, and completely symmetrical A1G orbital. So it's just this. And you can write EG1 or EG2, but you can write also the here you should put I, sorry, it's a complex linear combination. EG plus and EG minus is the complex combination of these two orbitals, and in that case it will be also the representation for spin-orbit interaction. Okay, so since I told you that spin-orbit coupling can be important in vanadium oxides, or it's really important in some big system, now everybody is talking about halogen insulator, where spin-orbit coupling is an important ingredient, or in iridates, where it's also very important. But maybe in vanadates, spin-orbit coupling is not the strongest interaction, but still can be important, and sometimes it's really needed in order to understand the physics. So I show you different kind of crystal field, and let's see in which of the cases spin-orbit coupling will be important and will be active. So if we have flattening on the axis, so this is tetragonal distortion, I still have the cubic orbitals, then in principle I can further split. So Yantelia theorem is telling me that whenever I have orbital degeneracy in the system would prefer to further distort in order to remove this orbital degeneracy. And you see, if I have two electrons, like in vanadium 3 class, and I have this sign of tetragonal distortion, I still have some degeneracy left, and this is degeneracy in this doublet. How I can split this? Yes, I can think about spin-orbit coupling, and in that case, xy orbital would correspond to Lz equal to 0, and these levels, they can be further split. So 1 lambda down, 1 lambda up, and that would correspond to z projections of orbital angular momentum plus minus 1. So by this we can still gain the energy and remove the orbital degeneracy. Okay, so this is the eigenrepresentation for Lz plus minus 1. Okay, so if I have the opposite sign of tetragonal distortion, then I have two electrons, I put them in this doublet, and there is no sense to distort them anymore. They are already in the lowest energy state, and there is no degeneracy. So if distortion is in this case, this has this sign, then spin-orbit coupling is actually ineffective. But if you would be describing, for example, titanate, where you have only 1 d electrons, in that case, you will have 1 electron here, and you can further distort. So actually, the sign of distortion usually knows about possibility to further split due to spin-orbit coupling. So this is the case when we have this trigonal distortion, and basically the same story. We can further split if the sign of distortion is like this, and we cannot split, spin-orbit coupling is ineffective in this case. Okay, so how we describe system where we have more than one orbit? So in principle that happens not only in insulators but in metals as well. So we start with a multi-band Hubbard model, and depending how many orbitals are degenerate and active, we will put here different alpha and beta that will correspond to the orbital E. So in metals, and that was already discussed here by Matthias Wolter, so basically orbital degrees of freedom or many bands can lead to the orbital selective mode transition, and this is the picture from Lucas' paper and cohorts. And basically, what they did, they considered a free-band Hubbard model, studied the EMFT plus exact generalization, and then they see that while in the blue band there is certain insulating behavior, there is some weight in the other two bands, and at certain value of U, we see that one orbital become insulating while the other two still shows metallic behavior. But I'm not going to discuss metals. He's here, many other people are studying them, so it's just an example. What I'm discussing is mostly mode insulator. So in that case, I can say that all my matrix elements, my hopping or my bandwidth is small compared to this U, alpha, beta, whatever. It's all local interactions. It's Coulomb interaction, it's Hund coupling. And in that case, in order to obtain a relevant description of the spin and orbital degrees of freedom, I should obtain a Kugel-Homsky model. And in the simplest case, you obtain by doing the second order perturbation in the hopping. Sometimes if the lattice is complicated, you have to go to higher orders. But in any case, what is important that this Hamiltonian describes at the same level of footing 2 degrees of freedom, both spins and orbitals. So here you have a spin exchange, and here is some pseudospin exchange. Since pseudospins do not need to have the proper symmetry, let's put it like this, and can be K2 would describe just the orbital change. And already from this Hamiltonian, we see that there is certain interplay between spin and orbital degrees of freedom. It's very nice if they have different energy scales. In that case, you can average 1 degree of freedom and look to the dynamics or to the properties of another one. Sometimes you cannot do it. So the problem itself can be very complicated. And if the lattice is complicated, also to compute all the contribution in the proper Kugel-Homsky Hamiltonian is quite a bit of work. But this is the proper way to describe spin orbital system. Okay, so that's more or less the end of the introduction, and here are the system I'm going to discuss. So all of them have can be described by general formula A, B2O4, so V is vanadium, 3 plus, spin equal to 1. And basically, if it's spinels, and in my case it's spin vanadium 204 and manganese vanadium 204, then in spinel there's 2 sublattice, A and B magnetic sublattice, and in A sublattice, in case of zinc, it will be non-magnetic zinc. In case of manganese vanadium 204, it will be magnetic manganese. It's a diamond lattice, and the crystal field is tetrahedral. The B sublattice, in this case, is vanadium sublattice, and it has octahedral ligand surroundings, and the lattice will be the pi-4 one. So in the calcium ferrite structure, calcium vanadium 204, calcium is big one in principle that would like to be spinel, but it cannot. So it distorts already at a very high temperature, and you have some unequivalent vanadium zigzag chains. Okay, here is the underlying structure, crystal structure. So, though in principle in manganese vanadium 204, we also should take into account that manganese is magnetic ion. So for vanadium, it's the Paracor lattice. And the Paracor lattice is known to be the most geometrically frustrated lattice. So if it would be only spin degrees of freedom, like in chromium, then the system can remain spin liquid down to very, very low temperature when some small interaction break with the germs. So in calcium vanadate, you can see these zigzag chains, actually unequivalent, and this structure is also degenerate. But here degeneracy comes from the fact that nearest neighbor and second neighbor are more or less at the same distance, and therefore if you forget about orbital degrees of freedom, that would be G1, G2 model where G1 is equal to G2, and this spin chain is known to be frustrated. So the ground state is disordered one. Okay, let me go one by one, but before discussing some experimental facts, in all these systems there is always two phase transition. Basically, in all insulated vanadium atoms. And that's one of the indications that you have 2 degrees of freedom, and probably they have different energy scale, 1 degrees of freedom order at 1 temperature, for example, orbitals first, and another degrees of freedom can order X at different energy. So in thick vanadate, we have 2 transitions quite close. So the first transition, the symmetry changed from cubical to tetragonal, and the second transition is a magnetic one. And basically, the structure is the following. So you have one-dimensional chain lying in the XY plane, and here you have spins down, up, and you have also spin chains in XZ and YZ direction, where you have up, down structure, and this cross really shows that the excitation, that's from inelastic neutron scattering measurement of the group of Bell Lake, and that really shows that you have nice one-dimensional chains. And Yasuki Kato here presenting the poster discussing the peculiarity of this structure. Please come to this poster. What I want to say that at least we should understand a few things about this compound is that these chains, which in the mean field you can look at this chain in one XY plane and the chain in another XY plane, they are orthogonal, so in the mean field sense they are completely degenerate, and you can see that in principle in three-dimensional structure you have a formation of one-dimensional object. And yes,
this cross, was it really obtained for zinc vanadate or for magnesium?
For magnesium vanadate, because they don't have single crystal for zinc vanadate.
No,
but
because maybe they managed to
no. Okay, so sorry for the confusion, but since I'm not going to discuss it in details, so there is another compound which has recently been synthesized as a single crystal, and they measure on magnesium vanadium 204, but from vanadium point of view, it's exactly the same. So this one-dimensionality, can we understand how orbitals have formation of this one-dimensional structure? The answer is yes. There are many questions about this compound, but at least this is certainly clear. The first transition, if you saw, it's a structural transition. And at this structural transition, tetragonal distortion takes place, and XY orbital is the lowest one, so that means that we have a flattening of the tetrahedron. So XY orbitals is occupied at each side. Even though the big question what happens with the second electron, how this degeneracy is removed, once again you can look to the poster of Yasuki Kato about this question. But this XY orbital, I have to say one more thing. So in the Perkins structure, the structure is such that you have H-sharing vanadium oxygen chains, and in that case what is important is that the exchange between 2 different vanadiums, the main contribution is direct exchange, because the vanadium oxygen vanadium bond is 90 degrees, and for T2G orbitals, if this angle is strictly 90 degrees, then that will produce zero exchange. Okay, but okay, if it's slightly distorted, it will give you some contribution into exchange, but it's a small one. Let's forget about it. So what is important is that we can consider the direct overlap between T2G orbitals. They are also quite close. It's about less than 3 angstrom, the distance between them. And if from this T2G overlap, we take only the maximum one, it's this one, when these flowers lobes towards each other, and this kind of overlap is called DD sigma overlap, then that means that orbital degrees of freedom, so if some electrons are carrying the orbital flavor XY, it can hold only along XY chain, and it cannot change its orbital index. What does it tell us? It tells us that orbital degrees of freedom in such structure are static objects, completely classical static objects, and therefore they can be expressed through projectors. That means from the whole pseudospin description, only its Z component will matter. So if it will be just 2 levels, it will be like IZ variables. So now side, and another one here. And we know that it's the same way how the Heisenberg exchange can be obtained from the one orbital case by gaining the kinetic energy. The antiferromagnetic exchange is established. So the strong exchange is antiferromagnetic one, and this strong exchange actually explains why these quasi or one-dimensional structures are formed on the completely three-dimensional parabol lines. Okay, I mentioned the trigonal distortion, and the trigonal distortion apparently play a role in a different compound. So it's manganese vanadium 204. Overall, the structure is the same, except that manganese carries spin 5½ and basically the interaction between manganese and vanadium explain the first transition, which happened at 56 Kelvin. And the first transition is actually you have the ferrimagnetic structure, so it's actually antiferromagnet. So manganese and vanadium, they look in the opposite direction, but vanadium has spin 1, manganese has spin 5½, so therefore it's a ferrimagnet. And then, a little bit below, at 53 Kelvin, the second transition took place. And this transition is quite difficult to understand because at this transition, what they see that the XY component, so at first transition you have only the ordering of the, let's say, Z component, but at the second transition what you see that 90-degree structure, orthogonal structure took place. And the question is how the orbitals, what happens with orbitals that they support such structure? Obviously, if no orbital, there is no way to explain the appearance of such a 90 degrees structure. And I start discussing this because actually trigonal distortion. So it's important that in the particle lattice or in the spin elevator to say even at the high temperature there is very strong trigonal component in the distortion. So even if the overall symmetry is more or less cubic, locally the trigonal distortion is quite important. Okay, so our idea was let's do some approximation. Let's think that trigonal distortion is the strongest interaction. Probably that's not true because we know that overall there is also tetragonal component. But if we take these two distortions and mix them together, as we know that oranges and apples mixed together do not help to understand anything. So let's start with oranges and let's look what kind of physics trigonal distortion brings. As I said, in this case it's like this, and we have to go to chiral bases, e.g. plus e.g. minus and a1g, and all these mu are this direction of this local trigonal axis. And once again, what is important is that they look at the different direction. The evidence that in this particular compound the trigonal distortion is indeed very strong come both from NMR experiment of Chung, and it was also shown, and I think it was first shown from ab initio calculation by the group of Roser Valenti in this paper, Sarkar et al. So we just start from this and we look what it brings us. So basically, the Kugler-Homsky-Hamiltonian in this case can be written like this. Don't put much attention into details. If you want to know how to obtain it, I can certainly explain. But what is important that, once again, here A1G orbital is always occupied, and the degeneracy, the orbital degeneracy, is actually in this EG manifold. So there is 2 electrons. And if we are interested in orbital degrees of freedom only for the moment, then basically we can go into these 2 electron bases, and our degeneracy is in this doublet. Okay? So in this case, what we have to do, we have to write this P alpha I and P alpha J corresponds to the projectors, to the orbital states alpha, at side I or side J. So it's projectors. Once again, it's projectors. It's like Ising variables. So if I do it, I can write my orbital projectors in the presence of strong trigonal distortion in this form, where this NYZ would describe, actually it will, it's once again this circle which you see already in the urine talk. So we have doublet. doublet is described by Pauli matrices. So now in the parallel lattice, in any case, we have three types of bonds. The bonds which are diagonal in xy plane, in xz plane, and yz plane. And now we just introduce some unit vectors which at the end will somehow tell us what kind of bond we consider. And we see how our orbital degrees of freedom, how our pseudo-spin, which is, you can always write it in terms of Pauli matrices, is distributed between different bonds. So if you do this, you take these projectors and just substitute it into the super exchange, and you assume that, let's for the moment forget about spin degrees of freedom and either say that we are in the ordered state or in the paramagnetic phase, but we know what to do with the average of the SI-SJ projection. In that case, the super exchange Hamiltonian, which will describe orbital degrees of freedom, will be this one. And since many people ask questions to students, you remember this Hamiltonian? You saw it already. What is this Hamiltonian? The chairman showed you this Hamiltonian. That is nothing else as 120 degrees orbital mode. But he showed it in the for the EG orbitals and on the cubic lattice, and he described the degeneracy of this model in cubic lattice due to some possibility to make some energy costless rotation of certain parts of the lattice. And Christian was studying this this Hamiltonian and many other people, so I will not give any reference here. It was all presented by Jeroen. I want to say that in our case, this 120 degrees orbital models appeared for T2G orbitals and on the parallel lattice, and it's not frustrated. In a sense, it's not frustrated, and I will not go into discussion of ground state of this model. It's not frustrated in the sense that it has only discrete symmetry, and actually you have 6 states, and they all have the same symmetry. But you can find basically the classical ground state of this model, and it's not degenerate. There is no continuous degeneracy. Why? Because on the parallel lattice, there is no object. Due to the connectivity of the lattice, you cannot choose a certain part of the lattice, rotate it, and that would cause you no energy. Not because you cannot rotate it, but because this object just doesn't exist in the non-bipartite lattice. Okay, why I spoke about this. So once you obtain this model and study the ground state of this model, basically what it tells you that one of the ground state is such that you have these chains, which you saw already before in XY planes, but now it's not spin chains, it's orbital chains. And they are characterized, so one chain will be characterized by the orbital tau y equal to -1, another would be 1, so it's a staggered ordering in the orbital sector, and you can write the corresponding orbital wave function. What is important is that once you write this wave function, you see this mu x, mu y, and mu z. And this mu x, mu y, and mu z, even if you are going along the same chain, which are characterized by the same orbital order, the axis of the trigonal axis, the direction of the trigonal axis will be rotated from side to side. And that you will know, so you have some plus and minus signs which will change, and that is this new numbers here. So what was also found in this ab initio calculation was actually very intriguing. What they say that apart that there is an orbital change, one-dimensional orbital change, there is also a certain modulation of electron density along these chains. And we just compute this electron density. We should remember that in this integration, we should remember that we have 2 electrons, so this is how we should do it. And basically, once you do this calculation, you obtain that you have some part which would be the same for all the sides along. Let's say we consider the orbital chain, which consists of 0 and 3 sides. So these would be the same. And it will be also some part in the electron density which will have different sign for site 0 and site 3. So it will be some certain modulation or staggered path in the electron density. And that's exactly what they found by doing their initial calculation. What is the reason for this? The reason for this is this different plus and minuses in mu x, mu y, mu z, which just tells that the direction of the trigonal axis at site 0 and the direction of the local trigonal axis at site 3, they are opposite. They are looking in different directions. Okay, so here trigonal distortion is responsible for formation of one-dimensional orbital chain and modulation of electron density along this chain. In the same compound, this helps to explain this 90 degrees orthogonal spin order, and basically what we did, we looked to the limit when this trigonal distortion is the strongest one, but we also have some orbital exchange, g tau, and we have spin-orbit coupling. If you do perturbation theory, then the competition of these two interactions produce you some staggered spin anisotropy, such that at different sites, 0 and 3, it will have, at a different, orbital chains, it will have different directions. So if tau y is +1, then the spin will be looking along y direction, and if it will be -1, then it will be looking in the x direction. So we get the staggered anisotropy, which actually explain this 90 degrees structure. Here there is two cases. Actually, the difference is that in one case you take into account non-magnetic, that the A sides are occupied by magnetic ions. Manganese has spin pi-half, and in another case not. But what is important that in both cases this staggered anisotropy produce orthogonal structure. Okay, that's one more example. Once again, I will not go into detail. So this calcium vanadium 204 is this distorted structure when you have zigzag chains, and I showed you this before. What is important that the ordering in this zigzag chain is quite complicated, and once again there is two transitions, the first one and the second one a little bit more apart, and once again orbital degrees of freedom are important. And interesting thing that here the quasi one-dimensionality in the spin structure is already at the first place, it's already at the high temperature, and it's again the same reason, already at the high temperature of carbon distortion.
Maybe one question at the previous one. What is then the main difference between manganese and zinc?
So if you think from this picture, no, it's actually that.
Or manganese itself.
Hmm?
Because magnetism of manganese itself kind of didn't enter the water. Right?
No, it's entered. I just didn't show it.
So what's really more important? Manganese magnetism, that manganese is magnetic, or different degree of trigonal distortion? You compare, say, zinc and manganese.
Okay, so if so, the first question is that in zinc vanadium 204, the measured trigonal distortion is, I mean, it's not measured. Trigonal distortion is very difficult. The estimated trigonal distortion is much smaller than in manganese. I'm sure that zinc and manganese has different sites, okay? So they produce different distortion. The first transition in this compound cannot be explained without taking into account the exchange between manganese ions and manganese spins and vanadium spins. But here, if you want to obtain this 90 degree structure, this is the correct structure, but in principle it doesn't matter. And once again, our calculations were done in the limited cases where we start from the trigonal basis. So we start from the assumption that trigonal distortion is the most important interaction, and all the rest just comes afterwards. It's an assumption.
For this story, manganese magnetism is not relevant.
It's not irrelevant because, I mean, it's also the spin distribution. If it would be just zinc, then the vanadium itself, they would try to order the Z component of vanadium spins, they would try to couple oppositely, up and down, so they will have antiferromagnetic line. And that's this point and the cross. In the manganese case, the points means that the Z component of the vanadium spins look at the same direction. Why? Because of exchange with a strong field, let's say,
No,
produced by magnets.
I mean just this very presence of 90-degree structure.
No,
That for that magnetic is not relevant.
no.
Correct?
At least at the level of our calculation. Okay, so this is the zigzag structure, less frustrated. And once again, we were working about this. We were looking for the orbital and ground spin degrees of freedom. Once again, I will be happy to talk about this. The reference are here. But what is important is that once again, you have spin degrees of freedom, and you can think about what is the interaction between spin degrees of freedom, and there is orbital degrees of freedom. So you can divide your model into different terms, and that's the decoupled system. Then you will try to understand what's actually coupled spin and orbital degrees of freedom. So from exchange point of view, from the Hooger-Komsky-Hamiltonian point of view, and all this enters in this second term, and there is also single ion interaction, distortions plus spin orbital. So it's basically for all spin orbital coupling, that's like the general trend how you try to analyze the system. What I want to say is, in any case, we can discuss various Hooger-Komsky-Hamiltonian in various lattices, depending on how many electrons we have different situations, but quite often you come to the situation that very few things you can say analytically. And we decided why not to try a toy model which will be somehow motivated by these vanadium systems, but probably not exactly related to reality. And once again, it's the possible, let me just put everything back. And basically, we wanted to consider one-dimensional problem. And for one-dimensional problem, only two of these compounds give motivation. It's this calcium vanadate with the zigzag chains and zinc vanadate with the stride chains. And here, actually, the possible orbital degrees of freedom in these compounds. So in calcium vanadate, you can have either this kind of antiferromagnetic orbital ordering, or you can have like ferromagnetic orbital ordering along the same chain. Okay. So once again, details are not important. What is important is the nature of degrees of freedom. So spin spin 1, and therefore, if we consider one-dimensional model, then the spin 1 coupled by antiferromagnetic interaction, which usually comes from the fact that one orbital is occupied, and that's produced strong exchange. So this is nothing else as a Haldane spin chain, and that has been extensively studied, so we know quite a lot about this chain. So orbital degrees of freedom, because we consider only dd sigma overlap, and I said that in that case the orbital degrees of freedom are static, they can be described by Ising variables, especially in the case where either the trigonal distortion or the trigonal distortion are the largest one, so one orbital is splitted and always occupied, while the orbital degeneracy is come from the doublet. So it's described here, and we wanted to learn what is actually the role of spin-orbit coupling. So here it's nothing else as a spin-orbit coupling projected to this orbital doublet. And this orbital doublet described by this tau x. That would correspond in the language of the orbital angular momentum would correspond to LZ. So that is nothing else as LZ and Z, but LZ is written in terms of the orbital pseudospeed. So the symmetry of this model is quite low, and the SU2 symmetry of the Haldane chain is broken, and we have only U1 symmetry versus Z2. And we also have Z2 symmetry from the orbital chain, and I have to speed up a little bit. So I want to say that this toy model which we consider is quite different from the spin orbital model in one-dimensional chains which were extensively studied, and that was much more symmetrical case. So in that case, spins and pseudospins, they were all both corresponding to spin and pseudospin 1/2. And this Hamiltonian has much higher symmetry, is SU2 symmetry, which at some particular cases even become SU or 4 symmetric. Here's some references, but what I want to say, we don't have these symmetries, and therefore our ground state is quite different from this one. So this is the toy model which we studied, and details are here. Let me just point a few things. Let's start from the limit where we know everything. And the limit is then spin-orbit coupling is equal to 0, then my orbitals and spins, they do not talk to each other, and for spin 1 chain, everything is known. Okay, it's a Haldanean ground state, singlet ground state, and there is some Magnum excitation. They are triply degenerate, and there is a gap, and the gap is 0.41 J, and the gap is at Q equal to pi. So one can write the description of this model using nonlinear sigma model, and this we actually need, this description, we need to understand, to write also the spin-orbit coupling in terms of some bosonic terms. So phi describes this Z component of the bosons. Let's say that this boson or this magnum will soften first. So the Ising, if we want to describe the Ising chain, we can use the fermionic representation, and that's the standard way. We can do Jordan-Wigner transformation, and by this we can rewrite our pseudo-spin apparatus describing orbital degrees of freedom in terms of Jordan-Wigner fermions. What we do next, we switch on spin-orbit coupling and start to understand what happens with the system when lambda is small and can be treated perturbatively. So using this representation which I showed you before, we rewrote our toy model. It's look like this, and since both systems, the pseudo-spin system and the real spin system, at lambda equal to 0, they are both gapped phases, then I want to see how this gap will be closed due to the interaction. And for this we can compute the correction depending on which gap is larger, the magnum gap or the orbital gap is larger. Imagine first that the orbital gap is larger, that orbital interaction is the strongest one. We can look what corrections can be obtained for the magnum spectrum. And basically what you see that the self-energy is proportional to spin-orbit coupling, and this is the spin gap. So you see that delta naught, that is the Haldanean gap at the limit lambda equal to 0, will be closing when lambda will be growing. So at some critical values, the spin gap will close and we will have some magnetic order. We can do the same thing in the opposite limit if the orbital gap is smaller than the spin gap. We can see how the orbital gap will be renormalized by magnons, and for this we compute also self-energy. And what has happened that the excitation in the orbital sectors when lambda is equal to 0, oops.
That's a good one.
Yeah, I'm almost done, so I don't know how to keep it off. What I want to say is that one or another gap will be closed at some moment, okay? So, and this is actually how you can think about as an orbital phase diagram, as a, modal phase diagram. So, tau z will describe the orbital order, which at lambda equal to 0 is its maximum value because we have like ferromagnetic Ising chain, and then we start switching spin-orbit coupling, and you see that lambda C1 will correspond to the moment when the spin gap will be closed, and then this eta will describe the staggered magnetization, and since in our model they are linearly coupled, then it immediately comes to the non-zero order parameter tau x. So here, just 2 more minutes, 1 more minute, 2 more minutes, much. So here is the orbital exchange, and this is the spin gap. So if this corresponds to the case when the orbital exchange is much stronger than the spin exchange, and this case corresponds to the situation, then the spin exchange is the largest interaction. And in that case, you see that these two easing transitions, they can merge into one. And basically, this case corresponds to the most critical case. And this is the phase diagram. So this is an isotropic spin liquid. And isotropic in the sense that now it knows about orbitals. And here we will be near long-range order. That means that we have some non-zero static manipulation. Since I don't have time, this is the phase diagram. And the only thing I want to say that the orbital sector, which was completely classical, becomes quantum in the presence of spin-orbit coupling, and in the limit where these two easing transitions merge into one, basically we can get some gapless phase in the transition, and that's probably the equivalent of the monatomic Latimer liquid, but in the orbital sector. Okay, once again, if you have questions, I will be more than happy to answer them.
Okay, so we have 7 minutes for questions. Who has a question? Daniel?
Maybe I continue, maybe same question which I asked already. For zinc, let's say you did not include trigonal field. For manganese, you included both manganese magnetism and trigonal field. So what if you would consider a system like zinc vanadate with non-magnetic side but a strong trigonal field? What would be, in your opinion, or in your theory, what would be the ground state of the magnetic organ?
It will be once again, if trigonal splitting will be the strongest one, once again it will be a kind of orthogonal structure.
Would it be commensurate or incommensurate?
I think it will be commensurate, but I mean, commensurate versus incommensurate will be determined by the competition between what is strongest, spin-orbit coupling, orbital exchange, and trigonal splitting. So you have free interaction, and probably depending on the ratio between.
So what are the options?
I would say the structure should be commensurate, but
Spins lying, say, orthogonal, spins lying in which plane?
the orthogonality will be in xy plane.
So spins will lie in xy plane, and the chain
Not necessarily. The spin can also have a z component, like in manganese. It's not xy spins, but xy component of the spin will be.
What would you get in your theory, actually? Suppose you take the same kind of theoretical approach, but simply remove manganese spins. Then you have solution.
Okay.
What is the solution?
The solution will be orthogonal structure with with a staggered z component. Staggered z component and orthogonal structure in xy plane.
Okay.
Please.
But what is the experimental situation?
In which compound?
Yeah.
In the zinc vanadium 204, the experimental situation is that the spin are along z-axis, and this structure which I show you, that at the low temperature along xy chain it has up down ordering, and along xz and yz chain it has up down ordering. Okay, and the question why the modulation along this z direction is different, once again can be understood, and that's well explained in the poster of ICAM. And in the manganese vanadium 2, the situation is that there is two transitions, both has magnetic component. The first transition into the ferrimagnetic state, when all vanadium sides are parallel and they are antiparallel to manganese spins. And it's a ferrimagnetic state. And the second transition, that Z component of vanadium spin remain ferromagnetically ordered, while XY component form 90-degree structure.
And in this structure, by the way, what will be coupling, what will be ordering in third direction, x dy? We describe what happens in this xy chain. What will be coupling in third direction?
Do you mean that the z can also be in the minus z direction?
Now, in
No,
a z direction, I mean, in the z direction, the z component, if you go, will be always ferromagnetically coupled. But once you determine XY coupling, then it's only depend on the sign of on the direction of the local trigonal axis. Why? Once you know the direction of the trigonal axis, you know the component in the xy plane.
So it will be also kind of a 90-degree structure if you
Yes.
go along in the way.
Yes, yes. It only depends on this chain which you are looking, because then you just should move with the direction of local trigonal axis.
I have a question that maybe a bit outside what you discussed. So, I mean, you did an impressive job for these spinel vanadates, right? So, what would be next? What are the open problems in this? Do you have any? This is now, I would say, almost closed, right? So you solved the problems. What are the next problems?
I don't know if we solve the problems, but first of all, new system appears. Second, and there are also questions about cobaltates, rutinates, where you still have some kind of computation of this. But if you really want to see what is the role of spin-orbit coupling, you go to iridates. And now you have all the family of iridates with parabol structure, triagonal structure, honeycomb structure, and there you have a super exchange because you have 5D electrons. But in addition, you are in the limit where spin-orbit coupling is probably the strongest interaction. And there you should rethink about all of this in terms, okay, spin-orbit coupling is definitely the strongest interaction. And I should start with J moments and then obtain some effective Hamiltonians which would describe already this entangled decrease of freedom. Spin and orbital angular momentum will not be any more like two different quantities, and you will have one, which is this J moments. But then you obtain the anisotropic Hamiltonians for them, and then you study the physics there. I mean, that's next step. What would be step after the next step?
Any more questions, remarks? If not, then thanks again.